Welcome to our Form 3 Physics lesson. It's Teacher Nyangoya, and my email address is nyamirai2@gmail.com, and my phone number is already displayed on the screen. As you sit down to listen, you need to have some writing material so that you can be able to take points. We are in current electricity. The objectives of this topic is to define potential difference and state its SI unit, then measure the potential difference and current in a circuit. Then we shall verify Ohm's law, define resistance and state its SI unit, determine experimentally the voltage current relationship for various conductors, define EMF and explain internal resistance of the cell, derive the formula for the effective resistance of resistors in series and in parallel, then finally solve numerical problems involving Ohm's law, resistor in the series and parallel circuits. But for today, we will define potential difference, measure the potential difference and the current in a circuit, and then our next lesson will be from verifying Ohm's law, and then we proceed. Thank you. Now, electric current. Electric current refers to the rate of flow of charge. The movement of charged particles, called electrons, constitutes an electric current, and the conducting part through which electrons move is called electric circuit. Let me show you a demonstrator on one of the circuits we have created. We have a circuit here. We have two circuits. I only want us to look at our first circuit here. We have a switch here. We have a bulb. We have a cell here. Therefore, these are electrons. Then we close the switch. What will happen? Look at that. Electrons are moving. They move. If we open the switch, no electron moving. Do like that, you see electrons moving. The rate at which these electrons are moving is what we are calling current, electric current. So what were we saying? We're saying that the movement of charged particles, called electrons, constitutes to an electric current. So what you are seeing here as electrons moving is what constitutes to current. Those electrons moving. When the switch. Yes. The path through which electrons move is called an electric circuit. The path the electrons move is called an electric circuit. So this is the path they move. This path is what we are calling the electric circuit. So current is the rate of flow of charge. So it is charge over time, Q over T, where current is given in terms of symbol I and the charge Q and then time small t. So current is the rate of flow of charge, Q over T. The SI unit of electric current is the ampere, after a famous physicist called Marie Ampere. Coulomb per second. 1 coulomb per second, because charge is in coulombs, time is in seconds, so 1 coulomb per second gives us 1 ampere. So the submultiples of the ampere is milliampere, that is 10⁻³ amperes, microampere, that is 10⁻⁶ amperes. Yeah, those are submultiples of the ampere. Definition of the ampere. An ampere refers to an electric current that flows in a conductor when a charge of 1 coulomb flows per unit time. 1 coulomb flowing per unit time. As per the formula, coulomb per unit time, it is coulomb per second. 1 coulomb per second actually gives us the definition of what an ampere is. Therefore, we say an ampere refers to an electric current that flows in a conductor when a charge of 1 coulomb flows through per unit time. Total charge passing through a conductor in a circuit. Total charge passing through a point in a circuit. If any electrons pass through a point and that each electron carries charge E, then the total charge passing through the point is equal to a number of electrons times the charge they carry. Number of electrons multiplied by the charge they carry. So you can say if we want charge, it is I multiplied by T, the rate at which they flow, and then multiplied by time. So if you want passing charge, the charge. It's like we go back to this formula. If you want to find charge here, it is I times T. That's what we are calling charge passing through a point. So charge passing through a point is what we have said, it is current times time. And if you want to find current, it's very simple. This is charge, number of electrons passing times a single charge, what it carries, that is Q over T, where every charge carries 1.6 times 10 raised power of negative 19 coulombs. So if it is 5 electrons passing there, it is 5 times that, so that you know the charge. Then you divide by time. Calculate the amount of charge that passes through a point in 3 seconds if the current in the circuit is 0.5 amperes. Current 0.5, time 3 seconds. So you only substitute Q is equals to IT. I 0.5, T 3 seconds. So 3 multiplied by 0.5 gives you 1.5 coulombs. Can be able to do that one here in the sample. Let us time. You have a stopwatch with you. We want to see within 1 second or within 5 seconds. Can you say you have a stopwatch with you? Neither have a stopwatch. We can say we have a stopwatch so that we record how many electrons passes here in within 1 minute. Can we go 1 minute? We want to count within 1 minute. Can we just check within 1 minute? 1 minute and see how many electrons pass here. Here, this particular point. This particular point we close. Oh. That's how you count. You count. Until a minute. Then from there, you say those are the number of electrons multiplied by a single charge, then divided by the time, we will get current that flows there. Open the switch for that. So that is how we are able to measure or you can calculate by saying current times 3 seconds. If we say we had 1 second, let me show you here. If that was 1 second, or we say in 1 minute, let me first of all measure the current so that you can be able to know. The current here is 0.45 amperes. 0.45 amperes. So 0.45 amperes, if we want to know the charge, Q is always equal to IT. We want to say 1 minute is 60 seconds. 1 minute is 60 seconds. So we can be able to say that we have 0.45. You have a calculator, just take a calculator and calculate that. 0.45 times 60. So you have 27 columns that passes here within a minute. So if you want to find how many electrons are these, it is 27 divided by 1.6 times 10 raised power negative 19. You'll be able to know within 1 minute how many will be able to pass there. So that is how we measure charge. That is how we calculate charge. We have an exercise here. A current 0.08 amperes passes through a circuit 2.5 minutes. So convert this to seconds. What charge that passes? Q is equals to IT. Multiply and get that. Calculate the number of electrons passing through the point per second. Number of electrons. So whatever you have here, divide by 1.6 times 10 raised power of negative 19. Because we said a single charge measures 1.6 times 10 raised power of negative 19 coulombs. So what you have here is total charge, then you divide, you get the number of electrons. A current of 0.5 flows in a circuit. Determine the quantity of charge in 4 minutes. So 0.5 times 4 times 60, you get that. Yeah, so having done that, we want to move to measurement of electric current. Measurement of electric current. To measure current, we use an ammeter. This is a sample of the ammeter we have in our labs. We have one terminal here written 2.5 amperes, another one written 5 amperes, and then a positive terminal on the other side. This 5 represents the outer scale. 1, 2, 3, 4, 5. So whenever you have connected a wire here and you have connected against this 5 ampere, then when you are using, because the graduation is on the same line, then get to know that you are using the outer scale. And for you to do that, make sure you understand what is the accuracy of the outer scale, and to get the accuracy is to get a single division measures what? That is, how many divisions are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 measures 1 ampere. So every division is 0 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0. So whatever we have here is up to 1 decimal place. But if you have connected against 2.5, 2.5 is the inner scale. Implying that from here to there is 0.5. So every single division is 0.05. 0.05, 0.10, 0.15, 0.20, 0.25, 0. Like that. 30, 35, 40, 45, 50. So this deflector, this pointer here can point at this point here. So you see, when pointing here, it all relies on which scale you are using. A number of students have been making mistakes. You find they have connected the wire here. Instead of reading the bottom scale, they read the top. They have connected the wire on 5 ampere. Instead of reading the outer scale, they read. So it is very, very important to understand which terminal you are using during connection. So, and the most important thing, once you have identified the terminal you are using, understand the accuracy of the scale, so that if it points here now, you are using the 5 ampere, then you know this is 2.1, 0.2, 0.3, 0.4, 0.5. At this point here, it will read 2.5 if you are using the outer scale. But if you are using the inner scale, it will be 1.05, 1.1, 1.15, 1.2, 1.25. This one will be 1.25. The outer scale, it will be 2.5. I hope you understand on how to use. And you always have a screw here for the purposes of adjusting the accuracy. We have said the zero error, if any, should be rectified using the adjustment screw before using the ammeter. So you ensure this one here, if you rotate it, sometimes this one may be far below the 0 or above 0, so adjust until the pointer just points 0. The ammeter is connected always in series with the components in the circuit, since it is an instrument with the row resistance. So and a circuit like the example this one of ours here, you see, we connect it in series here when we bring it here, so that it is part of the conductor along this line here, and therefore it can be able to read. So you can see it is connection in series. You connect it in series. So it records. What is the current recording here? Let me just close the switch. What is the reading here? The reading is 0.45 amperes. Let us also connect the second circuit. You can also measure here 1.80. This is 0.45. You have seen that. Now we move to our. Always know that the ammeter is connected in series. So if this is a circuit representation, so there is a bulb, then we brought the ammeter along the line, It's always connected along the conductor, like what I've demonstrated here, along the conductor, Accuracy of the scale of the ammeter must be observed when recording, like what we have said here, which terminal you are using, the outer or the inner. Then now we have an exercise for us to just go through. Give the reading shown for both scales. I don't know whether it is very clear to you. It is pointing here. The outer scale is 5, the inner scale is 2.5. So we said the accuracy for the inner scale is 0.05, because this is 0.5, so a single division is 0.05. So for the inner scale, this will read 2.0. One division is 0.05, so 2.05. The outer scale, the accuracy is 0. Because from here up to here is 1 divided by 10, giving you 0.1.2. So we have already 4 here. So this one records 4.1. So this is for 4.1 for the scale of 5. I don't know, this was meant to be 5, not 0.5. So 4.1. The other one is 2.05. 2.05. This one also should have been 2.5. Oh, 0 to 2.5, 0 to 5, 0 to 2.5, 0 to 5. So this is 2.05. This is 4.1. Now the reading is here. Now take your time and read that. You take your time and read what you have seen. Take your time. So what is the scale reading for the case of 0 to 2.5? So this is 5. This is how many divisions? 1, 2, 3, 4, 5, 6, 7. 7 times 0.05 will be 0.35. Add 0.5, the answer will be 0.85. For the outer scale, 1, 1.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. See that? 1.7. Potential difference. Voltage. Electric potential difference between 2 points refers to work done in moving a column of charge from one point to another. Work done in moving this charge from here up to here. Work done in moving a unit charge from one point to another is what we are calling potential difference. And we are saying that the measurement for potential difference is the volt. The battery is the source of power for moving charge through a circuit. It is through the battery here is the one that drives charge round the circuit. Without the battery, disconnect here. Let me just disconnect here, split. There will be nothing. So it is the one that drives charge around the circuit. So potential difference is work done in moving a unit charge. So it's work done over charge. Work done in joules divided by charge. So work in joules divided by charge in coulombs. 1 joule per coulomb gives us volt. In a moving charge, 30 coulombs from point B to A, 150 joules of the work was done. What is the decimal place between A and B? In moving a charge of 30 coulombs from point B to A, 150 joules of the work done, what is the decimal place between A and B? That's really not the decimal place. What is the potential difference between point A and B? Should be what? Should be the potential difference between point A and B. So potential difference is work done over charge, which is actually 150 divided by 30, giving you 5 volts. Definition of a volt. A volt is defined as energy needed to move 1 coulomb of charge from one point to another. 1 coulomb, because it's work done over charge. 1 coulomb of charge from one point to another. The same thing in measuring. This is how we do it. This is the same scale. Make sure you are the voltmeter is always written letter V, and the ammeter is always written letter A, though it's not indicated here, but it's always given letter A. This one is given letter B, letter V. So the same, get to know which scale you are using. The inner scale is 2.5, the outer scale is 5. So the same thing we have done for the ammeter. Potential difference is measured in volt. 0, if any, should be rectified using the adjustment screw before using the voltmeter. The voltmeter is connected across in parallel. Voltmeter is always connected in parallel because we want to know the potential difference between 2 points. It's connected in parallel simply because the instrument has got very high resistance, and therefore charge do not move here. It will only give us a difference of potential between this point and this point. So voltmeter is connected in parallel, ammeter is connected in series. Voltmeter is in parallel because of its high resistance. Ammeter is in series because of low resistance. An appropriate scale should be chosen during a measurement. We will come back when we shall be talking about Ohm's law. Accuracy of each scale must be observed when recording the readings. So can we be able to get the readings for this one? Like for example, the one of 0 to 5, 0 to 2.5. So 1, 2, 3, 4. 4 times 0.05, that gives you 0.2. When you add 0.2 here, that will be 1.70. The other one 3.1234. To read 3.4. Come to this one. The inner scale. 1, 2, 3, 4, 5, 6. 6 times 0.05. 0.05 times 6. That gives you 0.30. Add to 2.0. To 2.0, yes. That will be 2.30. For this one here, it will be 2.30. And for 0 to 5, 4.1, 0.5 here, 0.6 will be 4.6. I hope we got also this one correct, because 1, 2, 3, 4. 4, 0.05 times 4, it gives you 0.2. 0.2 add 1.5 gives you 1.7. That's how we are able to measure using these devices. For both the ammeter and the voltmeter, the negative terminal is connected to the negative terminal of the battery and the positive to the positive terminal of the battery. Now let's get this arrangement. Current and voltage in parallel and in parallel arrangement. We have this parallel arrangement. We want to know what is current 1 and what is current 2. The same setup. Go back and measure that. So we have always said ammeter is connected in series, but these bulbs are in parallel. So we come to the setup here. This one is in parallel, this one is in parallel. So let's take the ammeter and switch it on. Switch this one off. Then take the ammeter here. It will read 0.9 amperes. This one will read 0.9 amperes. Current 1 0.9 amperes, current 2 0.9 amperes. Current that flows across, total current 1.8. 0.9 plus 0.9 gives you 1.8. That is for the case of current. That is for the case of current. We want also to move for, so when the switch is closed, it is observed that the reading A1 plus reading A2 plus A3 gives the reading at A4. This plus this plus this gives this. Want to show that? So what is the total here? 1.8. So here 0.9. The other side here 0.9. Total 1.8. Correct? Through that. So therefore, the sum of current in parallel circuit is equal to the total current. The total current flows into a junction is equal to the total current getting out of the junction. That which moves into the junction is equal to that which gets out. Can we show that? What is getting into 1.8? What is getting out is 1.8. But there is a split here, 0.9, 0.9. What gets in is 1.8, what gets out is 1.8. Correct. Now, Now, we want to move to voltage. Voltage for the case of parallel. The voltage here, the voltage here, the voltage here. We have always said the voltmeter is connected in parallel. Come back here. Our voltmeter is here. So, this one here, connected here. 9 volts. This one here. This one here. 9 volts. At the cell here. At the cell here. 9 volts. 9 volts drop here. 9 volts. So it's like when electrons come here, you see, some go up, some go down. It does not mean that those go up again will come to pass here. No. So when they come, they go with 9 volts here. Some go with 9 volts here. So that's why the potential drop here is for 9 and the potential drop here is 9. Say that. Say, when the switch is closed, it is observed that V1 is equal to V2 is equal to V3 and is equal to the voltage that is coming from here. Therefore, for components in parallel arrangement, the same voltage drops across each of them since their terminals are in the same electric potential. Current voltage in series. So let's go to series setup. We want also to see the current in series. See setup is here. So we close this one. So go to this one here. Yeah, close this one. Current here 0.45. Current here 0.45. Current here 0.45. Current here 0.45. So current is the same. So let's see voltage. Voltage at this point here. .5. This point here, 4.5. You see, The voltage that comes here, 4.5 drops here and 4.5 drops here. The total voltage that is coming from here is what? 9. But this one is 4.5. This one is 4.5. 4.5 plus 4.5 makes what comes from the cell. That's what we are saying. When the switch is closed, it is observed that A1 is equal to A2 is equals to A3. Therefore, when components are connected in series, same current flows through the components, even if the components are not identical. When the switch is closed, it is observed that A1, A2, A3, they are equal. So they are from the same, the current is the same. Voltage, said for the case of voltage, it divides itself. What is here plus what is here plus what is here gives the total here. So we say the voltage switch, the switch is closed. It is observed that reading V1 plus V2 plus V3 gives us V4. Therefore, when components are connected in series, the sum of the voltage drop across the components is equal to the voltage supply. We have an exercise here for you to attempt using the diagram. The current passing through L1 in the figure is given that and diameter reads 1.2 amperes and L2 0.34 and L3 0.52. So you have the current here and current there. V1, V2 and V3 reading given that V reads 3.0. If V4 reads 3.0, what will be V1, what will be V2, what will be V3? We said that when it are in parallel like this will read 3, this will read 3, this will read 3. The only current that will be different here. In the circuit shown, what is the BD across the bulb and the switch? When we say you have 1.5 here, and the switch is open, BD across will be 1.5. When the switch is closed, this assignment will be coming part of your notes. Divine a volt. Make sure you attempt them and then work, take a photo and return them back. So I want to stop there for today so that our next topic now will be saying about Ohm's law, where we shall be looking at some funny things here that if we increase voltage, what happens to the resistance? Look at the figures, how they are alternating. When I minimize voltage, what happens with current? Resistance is constant. Voltage goes up, current goes down. Voltage goes down, current. What if we maintain? We now adjust resistance. We maintain voltage. Resistance goes up, current. So we will talk more about that in our next lesson, not now. I want to wish you the best as you stay home and wear your masks for purposes of ensuring that you'll be alive by the time you come back and we resume our normal lessons. Otherwise, thank you.